This video goes over finding the arc length for a curve in 3D space. The arc length between 2 points can be thought of as putting the first point at 0 on a number line and flattening out the curve to see where the second point would be. Recall the parametric arc length formula for a curve on a plane, where x and y are functions of t. Arc length L equals the integral from t equals a to t equals b of the square root of f prime of t squared plus g prime of t squared dt. Or instead of f prime and g prime, we could say dx dt and dy dt respectively. Remember that this comes from breaking the curve up into smaller sections, and the lines are connected between the points of each section. We can use the Pythagorean theorem to express the length of the line segments in terms of the change of x and y. That's where the structure of the formula comes from. Summing up the line segments gives you an approximation of the arc length. So, for the parametric arc length formula, the integral sums up the increments of changes of x and y along the curve, which change for infinitesimal increments of t, the parameter. For a curve in 3D space, we would be doing the Pythagorean theorem for a line segment that could change in the x, y, and z position. With z also being a function of t, z equals h of t, this would be the arc length formula for a curve in 3D space. This part accounts for the z direction. Now, remember r of t? Here's r prime of t. If you take the magnitude of r prime of t, you have the square root of the sum of each component's function squared. This means you can write the arc length formula with the magnitude of r prime of t. If you want to take it a step further, you can even use the velocity vector v, since that is r prime of t. So that's the formula for the arc length of a space curve. Let's do an example. Find the arc length of the curve r of t equals sine of 2t I hat plus 1 plus cosine of 2t j hat plus 2t k hat from t equals 2 to t equals 5. So here's our arc length formula, and we want to find L, which is the arc length. So first let's get r prime of t. R prime of t equals the derivative of r of t. So in the I hat direction, the derivative of sine of 2t is 2 times the cosine of 2t. In the j hat direction, the derivative of 1 plus cosine of 2t is negative 2 times the sine of 2t. And then in the k hat direction, the derivative of 2t is just 2. Now we need to take the magnitude of r prime of t. So we're going to take each component, we're going to square them, and then we sum them, and then we square root the sum. Going back to the formula, we want to know the arc length from t equals 2 to t equals 5. 2 and 5 are going to be our lower and upper bounds, respectively. 2 squared is a 4. We multiply that to the cosine of 2t squared. Then we add this to negative 2 squared is a 4. Then we have sine squared of 2t. And then 2 squared is a 4. And then we know with the Pythagorean identity that sine squared plus cosine squared equals 1. And then let's factor these 4's out. And now we have a cosine squared summed with a sine squared, and they both have the same argument inside. So this whole term is going to be a 1. So this turns out to be a radical 8. And now I'm going to evaluate the integral. The integral of a constant is the constant times the variable of integration. So we're going to have radical 8 times t, and we evaluate this from 2 to 5. So the arc length of the curve from t equals 2 to t equals 5 is 3 rad 8. Example 2. Find the point on the curve r of t that is a distance of 10 pi units from 900 in the direction of increasing t. And then r of t is given as 9 cosine t, 12t, 9 sine of t. Let's start with our arc length formula again. We're not trying to find the arc length in this case. We're trying to find a point. You don't need to draw anything to solve this problem, but I'm going to draw an arbitrary curve to label for reference. Let's say this is our curve. We're given a point 900, and let's say that the points go to the right as we increase the t values. If we travel in the direction of increasing t values for 10 pi units, let's say that this is 10 pi units, we want to know what the point is right here. So the 10 pi, that's actually the arc length L, and that's from t equals a to t equals b. So 900 is the point at t equals a. The thing is, we're not plugging in points into our lower and upper bounds, we're plugging in the t value. So we want to find the t value at which we get the point 900 on the curve. So at a certain t value, we have a vector which points to 900, and now we want to solve for what that t value is. So we're going to set r of t equals to 900, and then we can set the x, y, and z components equal to each other. In the x components function and the z components function, we have a cosine and a sine, and those are functions that oscillate. So we'll have multiple t values in which the x component equals 9 and the z component equals 0. Our y components function is linear, and if we solve for t, we'll get t equals 0. And if you plug this t value back into the x components function and the z components function, you would see that this t value fits for all three. So now we know when t equals 0, r equals 900. Now let's get the magnitude of r prime of t. So r prime is going to be negative 9 sine of t, 12, and 9 cosine of t. And then the magnitude of r prime of t. The magnitude of r prime of t ends up being 15. So let's go back to our arc length formula. L is 10 pi. This equals the integral from t equals 0 to t equals b of 15 dt. So now we can solve for b. The integral of 15 with respect to t is 15 times t. And we evaluate this from 0 to b. So we have 15b minus 0. And then if we isolate b, we'll find that b equals 2 pi over 3. Now we could find the point at which t equals b. Okay, so here's our vector going from the origin to b, and we now know that b equals 2 pi over 3. So if we start at the point 900 and go in the increasing t direction for 10 pi units, the point we end up on is negative 4.5, 8 pi, 9 rad 3 over 2. Now we're going to talk about arc length parameterization. S is the arc length function, and S is a function of t. This function allows us to calculate the arc length from a fixed point to a given t value. Let's reference the previous arc length formula. Previously, we would input two values of t to the bounds of the integral, and we could find the arc length of the curve between those two t values. Now we anchor the lower bound to a constant. This is usually t equals 0, and we call this t naught. The independent variable t is the upper bound, so this function gives the arc length from the starting point to a point at a given t value. By making the upper bound t, we have to change the t in the integrand to a dummy variable, which is usually tau or u. When we do integrate, we would plug the bounds into the variable of integration, so the tau disappears after the integral is computed, and the only variable that would remain is t. If you notice, this is an accumulation function. If we start at a point, s tells us how much distance we travel along the curve. Now let's do an example with that. Find the arc length function s of t for the curve r of t equals 2 times e to the t times cosine of t, 2 times e to the t times sine of t, e to the t. Then use the function to find the arc length from one t value to another t value. So let's start with the arc length function s of t. We want to get the magnitude of r prime of t again. So r prime of t equals the derivative of r of t. We can factor out a 2 for the first component, and then we have a product rule going on. The derivative of e to the t times cosine of t is e to the t, and then we take the derivative of cosine of t, negative sine of t, plus the derivative of e to the t, which is e to the t, and then we just write cosine of t. And then for the second component, we should have 2 e to the t cosine of t plus e to the t sine of t. And then the derivative of e to the t is just e to the t. We can factor out in e to the t, and then I'm going to rearrange cosine of t and sine of t. And then we could do the same thing for the second component. Now we need to take the magnitude of r prime of t. So we squared this component. 2 squared is 4. E to the t squared is e to the 2t. And then if we square the quantity of cosine of t minus sine of t, we would have cosine squared of t minus 2 times cosine t sine t plus sine squared of t. Remember, if you're squaring a product of two factors, you could square each factor individually and then multiply both of them. So now we add this to the second component squared. So 2 times e to the t all squared is 4e to the 2t. And then we need to square the quantity of cosine of t plus sine of t. This is cosine squared of t plus 2 cosine t sine t plus sine squared of t. And then we add our third component squared. And then that is all square rooted. We have a 4 times e to the 2t. This multiplies the negative 2 cosine t sine t. And then here we also have a 4 times e to the 2t. This gets multiplied into the 2 cosine t sine t. So essentially what we would have is a negative 8 times e to the 2t cosine t sine t. And we're going to be adding this with an 8 times e to the 2t cosine t sine t. So these two terms would just cancel out. Now we have a cosine squared plus a sine squared here and here. These equal 1. So we're left with a 4 times e to the 2t plus a 4 times e to the 2t. That gives us 8 e to the 2t. And then plus one more e to the 2t gives us 9 e to the 2t. We have the square root of 9 times e to the 2t. The square root of 9 is 3, and the square root of e to the 2t is e to the t. If it helps, you can think of a square root as raising a base to the half power. Now, specifically for the arc length function, we are going to have to change the t to a tau. So s of t equals the integral from t naught, which is t equals 0, to t of 3 e to the tau d tau. Now we can evaluate the integral. The integral of 3e to the tau is 3e to the tau, and we evaluate this from 0 to t. So this equals 3 times e to the t minus 3 times e to the 0. And then e to the 0 is a 1, so we just have 3 times e to the t minus 3. So after that, you could see how tau was just a placeholder variable. After we plugged in the bounds, we're left with t as our only variable in the equation. And then I miswrote this earlier. This is supposed to be t equals ln of 5. So now for part A, if we wanted to find the arc length between t equals 0 to t equals the ln of 5, all we need to do is plug in the ln of 5 into t. So we have s of the ln of 5 equals 3 times e to the ln of 5 minus 3. And then the e and the ln are inverses of each other, so we'll end up with 3 times 5, which is in the argument of the ln, minus 3. And this equals 12. So the arc length between t equals 0 to t equals the ln of 5 is 12 units. And then for parts B and C, you may be wondering, how would we use the arc length function to find the arc length between those two t values? So I'm going to draw a sketch. Let's say t equals 0 is right here. If you wanted to find the arc length between t equals 1 and t equals 2, how would we do that using the function? We find the arc length from 0 to 2, and then we subtract the arc length from 0 to 1. So to find the length between 2 points using the arc length function, L equals s of the final t value minus s of the initial t value. If your final t value is greater than your initial t value, then this difference would already compute a positive value. But in general, if you're finding the length between 2 points, length L would equal the absolute value of s of a t value minus s of another t value. Because remember, length cannot be negative. So for part B, if we wanted to find the length between t equals negative ln of 3 to t equals 0, we'll have s, we have the absolute value of s of negative ln of 3 minus s of 0. S of negative ln of 3 is 3 times e raised to the negative ln of 3 minus 3. And we subtract this by s of 0, which is 3 times e to the 0 minus 3. So before we can cancel out the e and the ln, we need to deal with the negative on the outside of the ln. That could be thought as a negative 1 being multiplied into the ln of 3. So using a logarithmic property, this can be written as 3 times e to the ln of 3 raised to the negative 1 power. And then 3 raised to the negative 1 power is 1 over 3, because you just reciprocate it. And now what we're left with is 3 times 1 over 3 minus 3. And then e to the 0 is a 1, so we have 3 times 1 minus 3, which is just a 0. And absolute value of ours. And this equals the absolute value of 1 minus 3, or just 2. And then C asks the arc length between t equals negative ln of 2 to t equals ln of 3. So again, with the absolute value bars, it doesn't matter if we do s of negative ln of 2 minus s of ln of 3 or the other way around. I'm going to do s of ln of 3 minus s of the negative ln of 2. Because ln of 3 is first and it is greater than the negative ln of 2, this difference is already going to compute a positive value, but in general, it's good practice to have the absolute value bars, so it doesn't matter which one you put first. So s of ln of 3 is 3 times e to the ln of 3 minus 3. And then we subtract this with s of negative ln of 2, which is 3 times e raised to the negative ln of 2 minus 3. And then we'll have 3 times 3 minus 3 minus, and then for the second part, we have to rewrite this using the same concept. This is 3 times e raised to the ln of 2 raised to the negative first power, or just 1 over 2. So the arc length between t equals negative ln of 2 and t equals ln of 3 equals 15 over 2. The next thing we're going to talk about is reparameterization. We know r of t. We get different vectors from the origin pointing to points on a curve as we vary t. And now we know s of t, the accumulation of arc length from an origin point on a curve to the point where r of t is pointing as we vary t. T is the parameter in both cases, as t is the independent variable. What we could do now is we can make s the parameter of r. After we find s of t, we can isolate t to get t as a function of s, t of s. We then can go back to r and get r of t of s, and the vectors pointing to the curve now depend on the arc length, so we can write it as r of s. For r of t, we would be asking, if we're at this t value, or in some applications, if we're at this time, where are we on the curve? For r of s now, we can ask, if we travel down this curve for this many units, where are we on this curve? Here, we can visually see that if we go 2 units in the forward direction from the starting point, we would be at this point. I'll show you this process in the next example. Alright, so for example 4, we want to find the arc length function s of t measured from t equals 0, and then for part B, reparameterize the curve r by arc length. So part A, that's pretty much what we did in example 3. So there's the arc length function. We're going to find r prime of t and then the magnitude of r prime of t. So going back to s of t, we'll have s of t equals the integral from 0 to t of radical 73 d tau. Taking the integral, we'll have radical 73 times tau, and we evaluate this from 0 to t. This just equals radical 73 times t. Part B asks to reparameterize the curve r by arc length. So we want r of s. We know the relationship between s and t. S equals square root of 73 times t. What we're going to do now is we're going to isolate t. So we'll have t equals s over rad 73. We can say this is t of s since t is in terms of s and t is a function of s. We're familiar with r of t. This is what we were given. Now we have t of s, and we can get r of t of s. Our original parameter was t. We now know what t is in terms of s. If we plug in s over radical 73 into each of the components t's, we'll get 4 cosine of 2 times s over radical 73 I hat plus 4 sine of 2 times s over radical 73 j hat plus 3s over radical 73 k hat. Since our r vector is now in terms of s's and not t's, this is r of s. And then here it is in component form as well. Now I'm going to show what we get when we take the derivative of r of s, which is really r of t of s. When we take the derivative of r of t of s, with the chain rule, we'll take the derivative of r, which is on the outside function, keep this argument the same, and then we multiply it by the derivative of the inside function. So this is Lagrange notation. Let me show you Leibniz notation. So this is taking the derivative of r with respect to s, and then r is a function of t. So we'll have dr dt, and then t is a function of s, so we'll have dt ds. dr dt in Lagrange notation is r prime of t. which is also v of t. And then we also have dt ds. So if we bring back up the arc length function, it's s of t. And then I'm using v instead of r prime. If we take the derivative of s with respect to t, we'll have s prime of t, also ds dt. And then we're taking the derivative of the accumulation function, and the variable of differentiation is a t, and that's on the upper bound of the accumulation function. And then, according to the fundamental theorem of calculus 1, we'll be left with the integrand, but with the upper bound t as the independent variable. The magnitude of velocity is speed. If we reciprocate both sides of ds dt and the magnitude of v of t, we'll have dt ds equal 1 over the magnitude of v of t. So the derivative of r with respect to s equals v of t times 1 over the magnitude of v of t. Remember that a vector divided by its magnitude is a unit vector. And then remember that v of t, the velocity vector, points tangent to the curve. If we make this vector point in the same direction but have a magnitude of 1, this would be the unit tangent vector t. The derivative of r with respect to s is capital T, and the magnitude of a unit vector is 1. And I will show you this using the r of s we found from the last example. Here's the r of s we found from example 4. Here's r prime of s, and then this is equal to the unit tangent vector. And if you take the magnitude of r prime of s, you would see that the magnitude of r prime of s does in fact equal 1.